In this video, we're looking at the energy stored in a simple harmonic oscillator and how it transfers forms. This applies to any simple harmonic oscillator that has a restoring force, because that's what they do, and we're going to use that to help think about this. You're going to want to have your packet ready when you're watching this video, because we're kind of going to go through an example in there. We know the period of various simple harmonic oscillators, and we found that by thinking about the sinusoidal nature of the motion in one dimension, and by thinking about the fact that the net force equals ma, and that the net force in this case is a restoring force that behaves like negative kx, just like a spring. We can also think a little bit further. If you think about a simple harmonic oscillator like this mass spring system on a horizontal frictionless surface, once you set it into motion, the kinetic energy and potential energy should swap back and forth, conserving mechanical energy, because only conservative forces are working, specifically the spring force. We're going to look at page 13 in your packet. So again, pause the video, pull this out. We're going to look at the spring potential energy, or the potential energy that is involved in general in a restoring force, the kinetic energy, and the total energy as functions of time. So we start with what we know as the position as a function of time, right? Xm, the amplitude, the maximum displacement, is equal to cosine of omega t plus phi. And that x can be plugged into the potential energy relationship for a spring. Now, the truth is you can do this for any simple harmonic oscillator. Notice instead of calling this US for U spring or spring potential, I'm calling it SHO, potential energy. Because any of our spring or pendulums or any other system that behaves with a restoring force, we can think of this K as being some combination of variables or constants for a given simple harmonic oscillator. So we can plug this in and we end up with U, the simple harmonic oscillator's potential energy as a function of time is 1/2 K x squared. And the X is going to give you your amplitude, your maximum X value squared, times cosine squared of that phase. We can, of course, think of the kinetic energy in a similar way. We also have an understanding of the velocity of a simple harmonic oscillator as a function of time. It's a negative sign function. We can plug that into, we can first square the velocity, which we can do. And we also know that omega squared is K over M, right? Something we learned in our previous analysis of this when we were looking at the period. And so we can plug everything into the kinetic energy function, 1/2 mv squared, where the mass is going to cancel out, and we end up with this 1/2 K times the maximum X squared, right? The maximum displacement times the sine squared function. We can then talk about the total mechanical energy by adding these two together, right? We're basically adding a sine squared and a cosine squared with a coefficient out front. And what, of course, sine squared plus cosine squared is 1. So we end up with a really simple formula for the total mechanical energy, which is a constant, which it should be, right? Conservation of energy, 1/2 K x max squared. So basically, if you think about this in terms of the mass spring system, what does that mean? Well, it means your total mechanical energy is the maximum spring potential energy, if you think about a mass spring system, when it's fully stretched. And that, of course, makes sense. That is where we would have zero kinetic energy in all potential. And that amount would stay constant as it oscillates. So what does this look like as a function of position? Well, this is mechanical energy max is at the top of our graph. Zero mechanical energy is at the bottom. We have a position showing us negative X and positive X max. So these are the amplitudes, the maximum displacement. So what I would say is pause the video for a second and think about what is the potential energy, kinetic energy, and total mechanical energy of our system as a function of position. Where is there zero kinetic energy? Where is there zero potential energy? And try to sketch that graph here, and then unpause the video and come back. So looking at this, we have potential energy is 1/2 kx squared. And so we can look at that. Mechanical energy max is going to happen at the max displacement or amplitude. And then we can fill in some values there, and you get sort of this parabolic, x squared relationship like that. We can then think about the total mechanical energy, which is just 1/2 K x max squared. And so that would be a horizontal line along the top. And then finally, we can say, well, what is the kinetic energy? Well, we could say it's 1/2 mv squared, or if it's one of these other formulas, but we don't really know exactly what that number is because we don't know v here. But we don't have to, because it is also, right, true that mechanical energy minus potential gives us kinetic, and so it fills in the missing piece. Now we can do the same thing, but instead of this being in function of position, we can do it as a function of time. So we have a quarter, a half, 3/4, and a full period, or a full cycle. Again, this time we're going to start with mechanical energy total. We know that's a constant. And then we're going to talk about potential energy, which is 1/2 k xm squared. So it should max out at all the energy, and times cosine squared of omega t. Now, cosine squared is going to always be positive and repeat more quickly than just cosine, but it looks like this, right? We have our maxima at 0, half a period, a full period, period and a half. We have our minima, our 0 is going to be happening at a quarter, 3/4, and so on, and we can fill it in. It's a little bit, it's too linear, but you get the basic idea. And then our kinetic energy, which is sine squared, is going to fill in the other part. All right, so hopefully that gives you an overview of what we're looking at with these graphs. So what does this mean in a mass spring system? Like, what do we think about this, right? If we have our potential energy, our kinetic energy, and our total mechanical energy, right, and we know that those have a relationship based on the conservation of energy, these apply to both horizontal and vertical spring mass systems. The big difference is that when you hang a mass, the equilibrium is at a lower point. The change in gravitational potential energy isn't a big deal. And so we can think about this in this way, right? If you stretch a spring, we get a change in potential energy. We pull down the mass by another thing from equilibrium. And we have our potential energy as a function of position, right? But what you'll see, if we go through the math, right, is that expanding them out, we have this term that has to do with the x naught. It cancels out. The x naught squareds cancel out as well. And you end up with this relationship, which if we think about what k is equal to, we end up with 1/2 kx squared plus mg over x naught times x naught, blah, 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 blah. Those cancel out again, and we're left with the change in potential energy is just 1/2 kx squared, where x is the amount by which it is displaced and doesn't really care about the initial position. Now, all of that derivation is nice, but mostly it's there to show you that you don't need to worry about the gravitational piece when you're in a vertical spring system, because it still behaves just in terms of 1/2 kx squared. As long as the x naught is our new equilibrium, right? We can't switch back and forth arbitrarily, but when we have something hanging on a mass on a spring vertically, as long as we call our equilibrium point 0, everything's fine.